And I guess for today's lecture, I thought it would be good to split it into two parts. Like one will be database content on FlowViz, where we talk about stream surfaces. And then the second part will be my recommendations for preparing for the exam. And to leave a few minutes at the end for module feedback, to encourage you to submit module feedback. What do you guys think of that? Does that sound like a reasonable plan? Any questions? I think my psychic powers are telling me that you're all wondering about the exam, right? Like, what can you tell us about the exam? Yeah, that's what you want. And I will, dedicate the second part of the lecture for that, because I have on my notes here the recipe for exam success written down here, which I will share. Yeah. But it's good if it's like kept in suspense until the second part. Suspense is very exciting. And the other thing you guys are wondering is, what's this, right? Anybody know what that thing is? What we're looking at there? There are multiple things going on there. But anybody want to guess what that thing is? You can make an educated guess, like an educated guess. You guys are the smart database guys. What do you guys think? What might that be?
Kind of looks like one and a half, like thing.
It actually says what it is on the text. An educated guess from somebody in this audience might be, oh, that looks like an isosurface to me. Well, a kind of special isosurface, right? A constant scalar value surface. That would be kind of an educated guess, but it is not an isosurface. It's actually the dual of an isosurface, which is a stream surface. So it is a surface that's everywhere tangent to a vector field, as opposed to a streamline, which is a curve that's everywhere tangent to the flow field. An isosurface is usually perpendicular to the vector field, actually, in a FlowViz application. So there's a surface there. It's hard to see the surface, though, because there's also a texture applied to the surface. So the surface is texture mapped, and the texture is moving. It's being advected in the direction of the flow. So it's a texture mapped stream surface where the texture shows the direction of the flow. We're not going to talk about the textures because we don't have enough time. We're just going to talk about the surfaces themselves. Hopefully we're going to talk about how to construct those surfaces. Okay, so last time we talked about the streamline seeding algorithm. I'm sure everybody remembers that really well. And today we're going to talk a little bit about terminology, stream ribbons, stream surfaces, and so on, and stream surface construction. So a streamline is a curve that's everywhere tangent to the flow. But that's limited, right? You cannot necessarily tell the downstream direction of the flow, and you don't get any information about the rotational properties of the flow necessarily unless you see them in a special way. We can extend the idea of a streamline to a stream ribbon, which has a fixed width. Basically, it's two streamlines. It's two streamlines, and those streamlines are computed in a fashion similar to our lecture on numerical integration. But the streamlines they show a twisting behavior because there's a triangle strip that tiles the space in between the streamlines. And then it gives it a surface, and that surface can rotate. So it shows the twisting, or sometimes called corkscrew motion of the flow. These are two stream ribbons here. And here is just a quick summary of one way to construct stream ribbons. So you start with a single seed point, and you integrate a streamline the same way you would without any other special knowledge. And then you choose another seed point that's a fixed distance away from the first one. And you integrate, so you integrate the first streamline, and you then integrate the second streamline. And then you have to do a normalization step, which is to make sure that the distance between these 2 points is always the same, whatever distance you specify. So you integrate, normalize, integrate, normalize, integrate, normalize. The streamlines will generally diverge, generally, not always. Sometimes they'll converge. But that's the idea. So integrate along both and then renormalize to make sure that they're not just, an infinite distance away from each other. We also have stream tubes, right? Instead of, with a stream ribbon, you could say we start with a seeding edge, right? Because it's 2 points and then an edge that connects the 2 points. With a stream tube, you can start with a polygon, an arbitrary polygon, right? And then integrate along all of the points along the polygon, so a number of streamlines. In this case, it looks like a 4-sided polygon, right? And this is going to show convergence in this direction and divergence of the flow a little bit more clearly than, say, a streamline. And if we don't normalize it too much, then we can show more information than a stream ribbon, right? Because a stream ribbon is really supposed to have a fixed width. So it shows the rotational properties, but not necessarily the divergent and convergent properties of the flow. This is just a little summary of the object dimensionality. So a streamline is you can say a streamline is a 1D curve, like an edge or a curve is usually called 1D. And the seeding object is a point, which is 0D, right? An extreme ribbon starts with an edge, which is a 1D line segment, and creates a 2.5D surface, you could say. Right? It's a surface. Same with a stream tube, except the seeding object is a 2D polygon. Could be a circle, for example, or it could be a square. And it also generates a surface. And we haven't mentioned stream surfaces yet, which we will, but they are seeded with a 2D curve, and they generate a 2.5D object. So stream surfaces are surfaces that are everywhere tangent to the vector field. We can summarize one algorithm. There are more than one algorithms for constructing these things, just like there are more than one algorithms for constructing stream lines and stream ribbons too. So streamlines are the most popular flow-based technique, or the most popular geometric flow-based technique. Remember, color mapping is really the most popular, and then vector glyphs are the second most popular. Those are direct. Streamlines are the most common geometric flow-based technique. Why? Here are some reasons why. They're not very difficult to implement, right? There's a formula we can follow. They're very intuitive, right? When we look at them, we understand them, generally speaking. And they're very applicable to all sorts of vector fields. These are some three-dimensional streamlines, by the way. And they're given a radius, so they look like tubes. They're not the same kind of stream tubes that we saw just a slide ago. They're just given a fixed radius, so they look like tubes, and that lets us apply shading. But streamlines have some disadvantages, like perception. If you were to seed 1,000 streamlines in a three-dimensional vector field, you would see a lot of clutter and complexity. If you don't do anything with the streamlines, it's hard to perceive the three-dimensional nature of them, right? Because it's more difficult to apply shading and lighting techniques. And therefore, without the shading and lighting, depth is more difficult to perceive. That's because curves, 1D curves, don't have a well-defined normal vector, which is the key property you need for lighting and shading. Also, seeding in 3 dimensions is still regarded as an unsolved problem. There are lots of seeding strategies for 2D flow fields, and there are some for 2.5D, not very many. And there are also for 3D, but this is for 3-dimensional vector fields, this is not really considered a solved problem. For stream surfaces, so it's a surface everywhere tangent to the flow. You can also think of it as the union of all streamlines seated along a curve. That's another way to define it. And it's extending the dimensionality of the curve to the next higher dimension. We won't really talk about path surfaces or streak surfaces because we don't have time. But the idea and the implementation of stream surfaces can be extended to unsteady flow. We're just going to talk about the steady state today. Here's a hand-drawn stream surface. Somebody drawing it manually. So conceptually, these stream surfaces have been around for a long time. Like in the world of fluid mechanics, the world of fluid mechanics has existed a lot longer than the field of data visualization. So fluid mechanics introduced this idea of stream surfaces a long time ago. And then they were brought into the world of data visualization around the year 1990-ish. So this is a hand-drawn stream surface. It's not that easy to understand. Like, it would be easier to understand if we could rotate this image. This is a computer-generated stream surface. So why would we want to even look at them? So one of the reasons is they have some good properties. One property is that flow cannot cross a stream surface because by definition the flow is tangent to the surface. The flow cannot pass through it, otherwise it wouldn't be a correct surface. Therefore, it divides up the vector field into different pieces of similar behavior. So it partitions the flow into regions of similar behavior. These are some stream surfaces, by the way. There aren't generally as many stream surfaces as there are streamlines in a visualization, so they reduce the visual clutter, or they reduce the visual complexity of compared with many streamlines. Surfaces have well-defined normal vectors, so it facilitates lighting and shading, something we know from computer graphics. And surfaces offer more rendering options. You can texture map surfaces, you can poke holes in them, you can do like more advanced lighting and shading surfaces, so they offer more rendering options. And that's why people like to have them around, as opposed to streamlines only. But they also have disadvantages. And one of the big disadvantages is to construct a stream surface is more complicated. It requires more difficult implementation than streamlines. They still suffer from occlusion, right? Multiple surfaces can hide one another. And placement of surfaces, or seating of surfaces is still considered to be an unsolved problem. Although the first person to ever write a PhD thesis on this topic graduated from Swansea University, Matt Edmonds, a few years ago. Actually, it was kind of a long time ago now. I think like 2011, maybe, something like that. So Matt Edmonds conquered this problem. He didn't conquer it so much that it's completely solved. There are still unsolved problems, but he was the first one to have a PhD thesis and offer some really great solutions to this problem. His was on placement, by the way. There was a different student named Tony McLaughlin working on the construction. The first stream surface construction algorithms used triangles. Just like what in that stream ribbon we saw a triangulation between these two streamlines. And this is sort of what the triangulation looked like. If you try to use triangles to construct stream surfaces, it gets very complicated. Right? Streamlines diverge, and you're trying to keep a tiling between the two streamlines. So you have to introduce new vertices if there's too much divergence, and you have to collapse some triangles and vertices if you get into areas of convergence. And when you tessellate the surface with triangles, you can see here it's trying to say this is a complicated. And it looks complicated, it looks chaotic in a lot of ways. So we're going to try to introduce a more intuitive algorithm for the construction of stream surfaces. You might see this term integral. Integral means it's based on integration. Remember, we to compute streamlines, path lines, and streak lines, we need numerical integration. So rather than using the term stream, path, or streak over and over again, just say integral. So we can consider the use of a surface composed of quads or quadrilaterals rather than triangles. And I don't know if you guys can see this, but this surface, can you see the little rectangles there? I don't know if that's possible. If you look closely at this surface, you can see that this surface is composed of rectangles as opposed to triangles. Usually, surfaces are composed of triangles, but this algorithm tries quadrilaterals to make the stream surface construction more simple, to simplify it. And that's what we're going to look at in the next few slides. So the properties, it uses quad primitives as opposed to triangles. All of the operations, the algorithmic operations, operate on a per quad basis, very analogous to the Marching cubes algorithm, which is also on a per cube basis. The data structures we use are simple. The parameterization of the surface is simple. And there are basically 3 operations and 3 algorithm parameters: desample, deadvance, and desep, which is analogous to the evenly spaced streamlines algorithm. Because these two algorithms have properties in common. So that the algorithm parameters resemble each other. In fact, DSEP is exactly the same. The DSEP parameter from the evenly spaced streamlines is exactly the same as this one. So here is an overview of the algorithm. You could call it the stream surface construction pipeline. So it starts with seeding a streamlines. Then we integrate, so we have a curve that we start with. We integrate streamlines along the curve a little bit, one integration step, as we saw in our numerical integration lecture. Then we test, we perform some tests. We're testing for divergence, streamlines that are moving away from each other, convergence, streamlines that are going to collide, and another one, rotation, so streamlines that are bending around one another. We test for those three conditions, and we make some adjustments if we find them. And then we test for termination, like should we stop the surface? If the answer is yes, we stop, right? And then we render the surface. Otherwise, we just iterate over and over again. Integrate, test for divergence, convergence, rotation, and keep going until we terminate. And these are the steps in more detail. This is what a streamline seeding curve looks like. It can be anything. It just happens to be an edge in this case. But this is typical, right? This is typical. The user has control over where to place this curve in space. They move it around in space. That's typical. It's an interactive seeding curve. And if you look carefully, you can see that there are streamlines emanating in the direction of the flow from that curve. And you can see an actual mesh. So that's the stream surface, but it's composed of a mesh, and you can see that the mesh is all quadrilaterals. So the curve has a position, it has an orientation, like you can twist it around in different axes, along different axes. It has a length, it has a number of seeds along the curve, so we have to specify the number of seeds. And the next step is to advance or start integrating each one of these streamlines. That's the next step. So the step one is position the seeding curve. Now the distance between, we also have to decide on the distance between these streamlines, and our distance has to be at least twice that of the signal that we're trying to reconstruct. In this case, the signal is provided by the data, the vector field data, and the spacing between the samples and the vector field data. So we have to space our streamlines at least twice the frequency. In other words, less than half the distance between samples in the vector field. And this is how we handle divergence. So in this diagram, these are two streamlines, and they're separated by DSEP initially. Right? This is streamline I, and this is streamline I plus 1. And this is the start position, and this is the next position along the streamlines. What we do to test for divergence, we run the test shown here. We look at the angles, the interior angles, alpha and beta. If both of those are greater than 90 degrees, and DSEP is greater than D sample, D sample is the space between data samples. Then we split the quad into two. We divide. So if these two angles are greater than 90 degrees and this distance is greater than D sample, the distance between data samples, then we split this bad boy into two quads. That means we introduce a new streamline seed here. We integrate a new streamline, and then this becomes half dSep, this becomes half dSep. We have two quads instead of one. And then from there on, we're integrating 3 streamlines instead of 2. By the way, this is the most common case. Divergence is the most common case by far. So it's a good one to handle. It's the simplest one as well. To handle convergence, is when 2 streamlines start to collide or get too close together. That results in oversampling or unnecessary computation. Again, we use 3 tests to test for convergence. One is the interior angle alpha. If that's less than 90 degrees, the interior alpha angle beta is less than 90 degrees, right? This is 90 degrees, a right angle. So you can see that alpha and beta in this case are less than 90 degrees. And this edge length here is less than half of D sample. So that's again the Nyquist limit. So this edge length is less than half of D sample. If we have a quad with the 2 quads with those configurations, then we merge them into 1 quad. So dSep here becomes dSep, right? And this streamline is terminated. That's basically what it just means. It just means test these angles, and if this distance is too short, stop integrating this streamline. It's essentially what it does. And merge the 2 quads together. That's convergence rather. And then the other case is curvature. So this is showing what happens to a mesh when it's curved. The quads start to become very deformed. And if they become too deformed, then the normal vectors to the surface start to become very unstable. The shading can be incorrect. It can be cause aliasing artifacts, and they'll show up on the surface. So how do we detect curvature? You probably could guess or make good educated guesses based on the previous 2 tests. But this is right curvature, in this right rotation, in this example. So we look for an angle alpha of less than 90 degrees and beta greater than 90 degrees. And then we reintegrate this streamline segment by a shorter distance, which is alpha divided by 90 degrees. So that is a heuristic. The alpha by 90 degrees is a heuristic. So as alpha gets smaller, the integration length of this streamline gets shorter, right? Because alpha shrinks, and this edge has to shrink accordingly. That's what this parameter is for. That coefficient, that kind of mysterious looking coefficient. And then we'll have a more evenly spaced quad mesh. We also have to handle splitting and termination. So this is a stream surface, right? And it's running into a wall. and it splits into two pieces that keep going independently. So when do we terminate? When we hit a critical point, that means zero velocity. The same is true for object intersection, which is also shows up as zero velocity. When we exit the domain, obviously, or if we just have a maximum length and we don't want the stream surface to spiral forever in some vortex, for example. By the way, this stream surface is color mapped. Can anybody guess what the color is mapped to in this case? Pressure? Anybody else have guesses? Velocity, magnitude, that's right. So slow flow is blue and faster flow is red. Right, that's the idea. So you can see it's going to slow down here because of there's something in the way. And then as the flow pushes the other flow out of the way, there's some kind of like a compression and an acceleration. So that's true about most of the images by default. If there's a color legend, then the color reflects velocity, magnitude. We can enhance, like we mentioned before, surfaces can be enhanced, so we can add interactive options, like where the user can control the length of the surface interactively. We can add timelines and time ribbons. I didn't mention what a timeline is yet. So looking back at our river example, I hope everybody can remember that. If we're on a bridge looking at a river, which we usually are. A timeline, imagine you have 5 people on the bridge standing next to each other and they all have buckets of popcorn. Imagine all 5 people taking on one piece of popcorn, dropping it all at the same time into the river. They all hit the river surface at the same time, but they're in 5 different positions. Then you connect those pieces of popcorn with a line, with a polyline or an edge. That's a timeline. And you release it into the flow, it all moves together. Because it reflects objects that were seated all at the same time, but not necessarily in the same position in space. We can texture map the surfaces. Right here are stream arrows that show the downstream direction of the flow. We can recreate the evenly spaced streamline algorithm as well, render flow lines on top of the surface, and so on. So here's a demo video of some of these things. This is what stream surfaces look like in action, so to speak. So that's the stream surface painter. That's the user adjusting the geodesic length of the stream surface interactively. And that shows you what it looks like to integrate a stream surface, so to speak. And you can see that this one is only diverging. This is the color map by velocity magnitude again. Those are the underlying quads and their different properties like divergence, convergence, left rotation, right rotation. This is texture mapping the stream surface with arrows to show the downstream direction. You can apply different kinds of textures, semi-transparent textures, completely transparent textures. And you can apply them at different resolutions. So you can see through the surface. You don't have to worry about occlusion. That's what happens. It looks like when you animate the surface, or the texture rather, on the surface to show downstream direction of the flow more clearly. You can see those areas of divergence, by the way, along the stream surface. And you can see where quads get divided into two. That's a more complicated stream surface, so there's lots of kinds of complex flow behavior there. And it's a big one too. It's big and complicated, that one. So that's the flow past a cylinder, by the way. The flow is moving past the cylinder. That's recreating the space streamlines algorithm in 3D. This is another property of, another byproduct of the algorithm showing timelines. So those are lines, curves that are all seated in the flow at the same time. And if we give them a width, we call them time ribbons. And the advantage of time ribbons is that you can apply shading to them. So these are animated time ribbons that show how the surface evolves, how the flow evolves over time. And the idea can be extended to unsteady flow. So a path surface is a surface everywhere tangent to a flow in the unsteady case. Now path surfaces can actually intersect itself. A path surface can intersect itself just like a streamline can intersect itself. I'm sorry, a path line can intersect itself. Any questions about stream surfaces? I did go a little bit quickly through that because I know everybody's waiting for the advice on exam preparation. That's what everybody is really excited about, right? Everything clear about the stream surface construction? The second part of the lecture is streak surface construction, but we will stop and not cover the streak surface. I do encourage you though to look at the videos on streak surfaces because they're so much fun. I can just show like a very quick streak surface video. I just can't resist. So we're not gonna, there's no streak surface material on the test. But it's so much fun to look at them, and they're so cool that I thought I would just show a little bit. So a streak surface is a dynamic surface. It applies to unsteady flow, and the whole surface has to be updated at every time step as the flow changes. So this is a simulation of flow past a block, and the streak surface changes, right, to reflect the properties of the flow as it moves past the block, and that's a time-dependent behavior. So the whole surface has to be updated. Every vertex has to be updated on the surface for every time step. In the stream surface and path surface case, the only vertices that had to be updated were the ones at the front. All the other ones just remained static. But this one is a much more complicated case where the whole surface has to be updated for every time step. So that the whole video is on YouTube if you want to have a look at that.